Okay, in this video, we look at page 2 of the radicals worksheet, okay? All right, so this is a pretty important little section here. Okay, so we're going to continue doing some more simplifying of radical expressions. So we pick up again with simplifying. The directions actually on this one say write in simplest radical form. Okay, so first I want to just kind of give you a way to think about it. What's going on with these is that instead of just having like the square root of 216, I have the square root of 216 x to the 9th. I have a variable in there. So that's what's different about this. You've done square roots involving numbers. You've done all sorts of them, but we're doing one involving that has variables underneath there. But the concept still holds. And if the exponent is small enough, you can just kind of think about it the same way we thought about simplifying 216. Okay, so we can take the 216 and break it down like we've learned to do. So 2 goes in there, 108. 2 goes in there, 54. We can kind of keep going until we get it completely broken down. So this one's kind of interesting. So it has 1, 2, 3 2s and 1, 2, 3 3s. That's 216. All right, so if we were just doing the square root of 216, if that's what we were looking for, the square root of 216, because it's square root, the index is 2, we'd be looking for pairs. So we have a pair of 2s. That's a way of identifying a perfect square. That would be 4. You could do the square root of 4, and that would give you a 2. So there'll be a 2 outside the radical. Here we have a pair of 3s. See how 3 times 3 is 9? So that means 9's a perfect square. You could do the square root of that, and you'd get 3. But then you see how this extra 2 and this extra 3 would still be underneath here? So you wind up with a 6 out in front, and then you wind up with a 6 underneath. Okay, now that's what would happen if all we were trying to do was simplify the square root of 216. We'd have 6 square root of 6, and that's it. We'd be done. Okay, but we got the variables to do as well. Okay, so because the 9 is small enough, I can get you to think about it this way. All right, let me go ahead and write all this here. So with 216, we had 3 2s and 3 3s, right? X to the 9th is 9 x's multiplied together, right? So we could think about it just like we did with our prime factorization, and we're trying to do a square root. So because the index is a 2, we're looking for pairs. So let's go through that again. And we've got a whole bunch of pairs of x's. Do you see that? Okay. So the pairs identify the perfect square. So we can bring a 2 out. We could bring a 3 out. And then we can bring out an x for each of these pairs. See that? So there'll be 4 x's out. We don't bring out 2 x's. X times x is x squared, which makes it a perfect square. So for each of these pairs, you're going to bring out 1 x. So there'll be an x for each of those pairs. For this pair, you can bring out a 2. For this pair, you can bring out a 3. All right, then you see how we'd have a 2 left, a 3 left, and an x left. So that would be a 2, a 3, and an x that would be trapped underneath still because there wasn't a pair. So this gives us a 6, and then x times itself 4 times would be to the 4th power, and then another 6 underneath here with an x. And all this is really multiplication in between. And the index is a 2, so I don't have to actually write the square. I can just leave it like that. Okay. Now, if we did a lot of this, we would want to observe things like how 4 of those pairs would have amounted to 8 x's. And so if we had done a lot of these, you might have, when you're looking at x to the 9th and trying to think about that, you could think about, well, x to the 8th, and then 1 left over. And you could think about how x to the 8th is a perfect square, but then you got the 1 left over. And so because there's 8 x's multiplied together, you have 4 pairs, and that's why you would get an x to the 4th. Okay, so there's a lot of things we could talk about if we had all day in the world, but because the 9 is small enough, you can kind of think it by just writing it all out. But I just wanted to mention that. Also, our idea with exponents can help. The reason that became a 4 is because that was x to the 8th raised to the 1/2 power. And see how that would become x to the 4th? Because a power raised to a power, you would multiply, and then you would just leave the square root of x underneath. Okay, so ponder that some more. Look at some more examples if you want. Okay, let's do another one. Okay, the next one involves a cube root. So this is number 10. It has the cube root of a negative 64 k to the 9th. All right, now this is something to be careful about. We've already had this happen before. A negative underneath the radical, like if you have a square root with a negative, then that's going to be an I. But if you have a cube root or a fifth root, okay, with a negative, those just lead you to a negative number. Okay. All right. So, and that's because like the cube root of 64 would be 4. We've had to deal with that already. 64 is 4 times 4 times 4. So 64 is 4 times 16, or 4 times 4 times 4. So see how there's 3 4s? So the cube root of 64, the cube root of 64 means we're looking for 3, and it would be a 4. We need a group of 3 of them to be able to bring anything out of the radical, and there's one group of 3 4s, so you can take a 4 out. So if you throw a negative inside there, what really happens is this can be negative 4 times negative 4 times negative 4. Okay. And that means the cube root would be a negative 4. You don't get an I, you get a negative number. So it turns out that negative 64, the cube root of it, would be negative 4. And then you've got all these k's. Okay. So let's look at that. So you might want to still think of it kind of like this. Okay. Kind of think about the 3 different types. This just gives you a negative number out in front. We just talked about how that's 3 4s. So the cube root would be a 4. And then here you might want to just visualize it since we can. There's 9 of these k's. Okay. This time we're looking for groups of 3. So we use them all up. Every one of them is a group of 3. So we can bring out outside of the radical 1 for each of these. But then there's no factors left. So our final answer on this one would be negative 4k to the 3rd. You also could see it kind of like I showed over here. An alternative way of seeing it is thinking about how we could take the k to the 9th, and instead of writing it like this, we could think about it in terms of exponents. And then these would get multiplied, and you see another way of seeing that it's going to be k to the 3rd. Okay. Now, if it had been cube root of k to the 10th, you would have had a k to the 3rd out in front, but there would have been a leftover k, wouldn't there? Think about that. If you had the cube root of k to the 10th, then you would have had like an extra. You would have had not just 9 k's, not just 3 groups. You'd have that leftover. So these would have been in a group, but this guy would have been left over. And if you had the cube root of k to the 11th, there would have been another k. Okay, so here's one group of 3, another group of 3, another group of 3. So that gives me the k to the 3rd. But there would have been 2 more that wouldn't quite make a group of 3, so they'd have to be left inside here. You see that? And then if I threw in a 12th one, then wouldn't I have, if I put in a 12th one, then wouldn't I have had an extra k. That gives me another set. That would have just been k to the fourth. Okay. All right, so that was question number, let me squeeze this down a little bit, make sure I wrote that. That was number 10, okay? So there you were doing cube root. All right, now number 11 is a square root. This is an important one to be sure you know how to do. All right, this is just a little bit of an extension over the square roots, and it's a little harder than number 9, just because there's more than one variable. All right, the exponents are getting a little larger, so if you're wanting to just kind of visualize that in your head, you can. But you might just take the 200 and break it down. All right, and you could go all the way to prime factorizations. And you finally get it down to being 3 2s and 2 5s. Okay. So 200 is 2 times 2 times 2 times 5 times 5. You could think of the k's, 11 of them. And think of the q's, there's 10 of them. And when the numbers are too big to really draw out, just remember these examples and see if you can't visualize what would happen. Really helps to picture this. All right, so look at your index. It's an assumed 2, which means you're interested in pairs of things. So you look for pairs. Okay, so all the q's are in a pair. And then on the k's, you got a leftover, don't you? But all the q's are paired up. See how the exponent's even? See how the 10 is divisible by 2, but 11 is not? That's part of it. See how 2 would have gone into 10 5 times? 1, 2, 3, 4, 5. But then the 11 is a leftover k. The 11th would be left over. 2 goes into 10 5 times. So we have 1, 2, 3, 4, 5 pairs. Okay. All right. So remember how we deal with this. For every pair, we can bring out the square root of it. So 2 times 2 is 4. Bring out just 1, 2. Bring out 1, 5. Here we have 1, 2, 3, 4, 5 k's. That'd be k to the 5th. This k would be trapped underneath. Okay. And then here we have 1, 2, 3, 4, 5 q's. 5 pairs of q's. So we could bring out 1 q for every pair. So 1 q for every pair. That would give us a q to the 5th, and then we have a 2 and a k left underneath here. So that would be 10 k to the 5th, q to the 5th, square root of 2k. All right. So it might have benefited you if I had done this. 5 can come out and then brought out 5 k's, 1 for each of those k's, and brought out the 5 q's. Okay. But those 5 k's would be k to the 5th. Those 5 q's would be q to the 5th. And then that's your final answer in simplest radical form. Okay. So when you're looking at ones like this with q to the 11th, you know it's q to the 10th with a leftover. And then if you were trying to do square roots, you can think about how these 10 k's would be all paired up. So there'd be 5 pairs, and then that k would be left over. So sometimes when I'm doing it, if I'm trying to do the square root of k to the 11th, this is what I actually think. And then I think about those 10 k's. I could have 5 pairs, so I can bring out a k for every pair, but then this k would be trapped underneath. So that's kind of a quicker way to do it. So when I was doing the square root of the q to the 10th, it was even. So they were all paired up and I didn't have anything left. I just had a q to the 5th, no radical on it. Okay. All right, well, let's try another one. Let's try a cube root. This is number 12. So this is a cube root. It has a 54, which is not a perfect cube, and then a to the 8th, b to the 5th. So let's see what happens there. Okay. So we can do it just completely broken down. All right, so 54 is 1, 2 times 3 threes. Then we have 8 A's. 1, 2, 3, 4, 5, 6, 7, 8 A's and 5 B's. So let's just think about it kind of intuitively. All right, we're doing cube roots, so we're looking for groups of 3. So here's a group of 3. Then there's only 2 A's left. I don't have enough for a group. Here's a group of 3. Then 2 B's left. So I don't have another group of 3. All right. So I can bring a 3 out, an A and another A, right? So I can bring out an A and another A. I've already brought out the 3. That gives me A squared. I can bring out 1 B, but then see how there's a 2 A's here and 2 B's here. So there's a 2, an A squared, and a B squared still trapped underneath. And I shouldn't leave so much space there because I don't want you to think it's a plus or something. It's just 3A squared B. That would be your final answer. Let me write it again. It's 3A squared B, and then it's the cube root of 2A squared B squared. All right, so it's a little harder to think about when you have an index that's bigger than 2, but it's not that bad. For instance, A to the 8th. I can think about how 3 doesn't, if I'm thinking groups of 3, it's like I'm thinking about how I have 8 A's there. Well, 6 of them would wind up being a perfect cube because I could pair them up. I could group them in groups of 3, and then wouldn't I have just 2 left? So if I'm trying to do cube root of 8, sometimes I think about it this way. And see how the 6 is a multiple of 3. So I could have 2 groups of 3 for that, and then I'd have these 2 left. Okay, so sometimes I do it like this, and since there's 2 groups of 3 there, I know that the cube root of A to the 6 would be A squared. But then this guy I can't do anything with, so he's trapped underneath. You see that? Okay, let's try B to the 5th. B to the 5th. Okay, so when I'm thinking about that, I can think about how many groups of 3. See how B to the 3rd would be a group of 3, but then I'd have 2 B's left. So if I'm doing the cube root of B to the 3rd would be B, but then I'd have 2 left. You see that? But if that were cube root of B to the 6th, then I would have had 2 groups of 3. So that's going to wind up working out to be B to the 2nd. If I had cube root of B to the 7th, you see how it's B to the 6th, but an extra B? So this part would be B to the 2nd, but then I'd have an extra B that I couldn't do anything with. All right, so we could do a whole lot more with that, but see if those 4 examples at least give you enough insight into how to think about it. The main thing I want you knowing is that if it's a cube root of 3, you need groups of 3 for something to be a perfect cube, for it to be able to be brought out from under the radical, okay? And if you know that, you can figure them out pretty good. All right, I'm going to go ahead and stop the video there, and then